So, die nächsten beiden Vortragenden darf ich auf Deutsch begrüßen. Herrn Pascal Kube von der Teijin Carbon Europe und Herrn Markus Hildebrandt von Inometa. Und Sie werden aber Ihren Vortrag auf Englisch halten, wenn ich das richtig verstanden habe. Viel Erfolg.
Wir möchten uns den Vorrednern anschließen und unseren Vortrag auch auf Englisch halten. Ich glaube, es ist für das allgemeine Verständnis ein bisschen einfacher und passender. Ich möchte mich kurz vorstellen. Mein Name ist Pascal Kube. Ich arbeite bei Teijin Carbon Europe als Application Engineer für Thermoplastic Materials. Und wir stellen heute gemeinsam unseren Vortrag vor über Laser-Assisted Tape Winding of High-Performance Tapes, Analyzing the Influence of Placement Speed. So Inometa and Teijin started a close cooperation to evaluate different types of thermoplastic tapes in their processing route to accelerate development times based on customer requests Inometa faces. We will first start with a quick company profile. So I will start with the Teijin introduction. Markus will take over with the introduction of Inometa. He will then move on with some motivation and partnership behind what we're doing and describes the systematic approach we're following. And I will then start over and show you some first results from our trials, give you some insights, what we evaluated, what we see, and how we move on, and what's furthermore planned. So Teijin Carbon Europe is part of Teijin Limited, a Japanese group, globally over 170 companies with more than 21,000 employees worldwide. I'm based in the German facility of Teijin Carbon Europe in Wuppertal. We also have our production plant in Heinsberg near the Dutch border. And we are one of the largest carbon fiber producers worldwide and are the largest short fiber producer. And on top of just the carbon fiber reduction, we also have various semi-finished products in our portfolio for demanding aerospace, automotive, or industrial applications, such as NCF materials, thermoset, prepregs, rapid cure systems, or thermoset prepregs based on rapid cure systems, but also our thermoplastic materials that is part of our evaluation. So what we call in Teijin language a TPUD, a thermoplastic unidirectional tape. In the portfolio we have several types based on high-performance thermoplastic materials, PEEK-based, low-mate PAEK, PPS, and also from the Japanese side some polyamide plants. And yeah, the first three that were mentioned are part of our evaluation process. And with our newest production line we have running since 2019, we are able to produce 24-inch wide tapes, but also the former standard with 12-inch and everything down to slitted tapes is currently handled by external partners. And yeah, the portfolio ranges fiber array rates from 100 to 190 GSM are possible. And with the new production line, thank you, we're able to produce up to 2,000 meters that can be as well sent directly to slitters, long defect raw materials that helps then automated processes as they are used within Inometa. Markus.
Okay, so my name is Markus Hildebrandt. I'm with Inometa and the Avanco Group since 2017, and I'm responsible for the thermoplastic winding activities that we do at Inometa. Maybe just to give you a short introduction to the company, since I would say we're not that prominent on the composite market yet. So we are located in Herford, Germany, have about 330 employees, and we've got a strong background in manufacturing high-end roller systems, which are made of aluminum and also of composites. And thus we have quite a broad range of composite tubulars, which we produce in filament winding as well as in thermoplastic tape winding, and a lot of know-how when it comes to machining those parts or even coating those parts. So based on this roller business, we decided to invest into thermoplastic winding machinery, which was supplied by AFPT, also here a company from Germany, in 2018. And we have, but we will show this today, different product categories that we are talking about. So we've got really thin wall shells, which can be used for rotor cans or rotor shells, for example. Here we are talking about really low amount of composite, but a large number of parts. that have to be produced, but on the other hand, there are other applications such as bearings, which have much higher wall thickness, thus more material per part. So that's quite a wide range of materials and quite range of geometries that we are looking at. So I would say the typical diameter range is somewhere between 10 millimeters and 400 millimeters, and part length are between just a few millimeters to 4.5 meters in length, which we can do in thermoplastic winding. Together with RFPT, we put just quite some work into this in order to get this process a bit closer to industry. So we have two completely autonomous winding axes. So one axis is always in the laser housing to be wound on, while the other one can be equipped with the next mandrel in order to get a higher degree of industrialization. In the end, Inometa is a producing company, so we are trying to produce series of parts, but we are also capable of doing some design for the composites as well as the post-processing. So we partnered with Teijin together because, and this is what I will show within the next slides, we have always run into the same problems with customer projects, since thermoplastic composites are quite new. Yeah, injection molding composites are out there for a long time, but continuous fiber reinforced thermoplastics tapes, their properties, what can be done with them, what can't be done with them, is mostly unknown to the customer. So, and the customer comes to us and he has a reliable solution. He has like a metallic solution or he has a thermoset solution, which oftentimes we are convinced that we can add additional benefits for those customers. But there's still development work to be done. Some customers don't want this development work, or they don't have the time to do this. And so we partnered with Teijin in order to get some of this development work done up front so that we can address the customer problems much faster and get into serious production much faster. So what have we done? So we are in the middle of these trials, I would say. You're there. So these are just some of the results that we are going to present today, but it's quite a simple approach. So we took the Teijin materials that Pascal already explained what they are. We did winding trials. We changed different of the key parameters. Today we are talking about a bit of winding speed, but there's also different winding patterns which occur in different applications. So there are a lot of parameters to be handled. We did just some on-site evaluation. So sometimes you can see this was not really a good setup, so we don't need to test the part. But when it comes to gaps within the laminate, overlaps in the laminate, that's something that normally we are doing together with the end customer for their application in order to get a really good set of robust process parameters for them. Aim of this partnership was to get an idea or as good as possible idea on what such a robust set of process parameters may look like in order to be quite fast in the development process, which is then customer specific. So I was reminded a bit by the talk of Markus with the automated programming. That's exactly these things. So there are different parameters which are different for each tape material, which are different for different geometries, and we just want to have a really robust base in order to choose these parameters, not make the end customer pay for our search for the right parameters. So, and then in the second part, that's what Pascal will present. We did some electrical evaluation, so DSC, microscopic fiber volume content measurements, in order to get for the materials from Teijin such a parameter sheet, which we then can use, maybe slightly adapt to the customer's final parts, and then be quicker in the development process. So maybe, to talk a bit about our experience which we had within the customer projects. So I would say the perfect world scenario for such a customer project is that the customer sends to us a specification for their part, which is perfectly suitable for thermoplastic composites, so they exactly know if they want PPS, PEG, PEEK, PP, whatever. They know what kind of tolerances can be reached. They are aware of the mechanical data. They are aware of cost structures that are out there in thermoplastic winding. But to be honest, that never really happens. So there are some projects out there where we are specifically asked for a carbon fiber peak bearing, for example, because this material is established for this one application, but 90% of the customer requests are not the thermoplastic winding specification that we get. What do we get then? So we get the customer specification, which is maybe from a metallic part, maybe from a thermoset part. So there are always the same questions arising when talking to the customers about thermal stability. So TG in thermoset is another understanding than TG in thermoplastic materials. So when dealing with thermoplastic materials, there's always the question about creep behavior. There's the question on how good are the tapes that are supplied on the market. So how's the porosity of those tapes? This leads to different applications where temperature is the driver, maybe corrosion resistance is the driver. Then sometimes the customer has a really narrow window on what angle he wants the fibers to be aligned in. Maybe this is technically possible, but then we have to work with really, really small tapes, narrow tapes, which then lets the production time go up and thus cost go up. So being able to give the customer a really an optimization on their customer specification, that's, I would say, the daily business with all of those customer requests we get. So it's quite an iterative process. This takes some time. This takes some trials. This is cost intensive for all parties. So what we are aiming at together with Teijin is to how can we shorten this adaptation process. So I think thermoplastic composites are not established in so many industries, so we can't get rid of this adaptation process, but we can try to optimize this adaptation process. And we want to use exactly this parameter sheet, which we are working on right now for the Teijin materials, in order to offer a unique understanding on how does this tape change through our thermoplastic winding process, and give those data to the customer, build trust with the customer in these new material class in order to get more wound thermoplastic applications out there in the market. So from here on, Pascal will take over and will present some of the results that we did with the PEEK material from Teijin.
Yeah, thank you. Thank you, Markus, for the quick introduction. What's the background of our work? I want to give you some insights of some first tries, so it's not all we did. So just the first review, let's say, how the iterative processing looks like, what we do. So here, the first results I will show you are based on one material option. It's a PEEK-based tape with an HTS fiber, so a high tenacity fiber. We also looked into low-met PEK material and PPS. That's still in the evaluation, and we have some other trials planned. The baseline, or the baseline part, the winded part, uses always the same layup. So it's 12 layers. First 90-degree layers, and then plus minus 45 around. But nevertheless, we also performed additional tries to see the effect if we change the winding angles, how it affects the gaps or voids between different layers. So that's all taken into account, and the trials are still running on that focus. First baseline was 15 meters per minute where we started. And on the next slide, I would like to show you when we do microscopic evaluation as a quick first insight to see how the consolidation quality is. First, an example of what we do not want to see in the tape, but with the quick cross sections we perform, we easily can get a quick feedback on some defects we clearly do not want to see in the material, such as porosity or voids between different layers, and as well, if you look below, gaps or overlaps, which then result as well in voids in the material, which clearly decrease the mechanical performance of the final application. So we did some trials and looked how the consolidation quality decreased or improved with different setups. So as I mentioned, we started with the 15 meters and then added for every trial another 5 meters per minute. So what you see here is the plus minus 45 that are the outer layers of the part. The plus minus 90 are in the middle. Below there is then the heated spindle that we use for the winding trials. And you clearly see, if you look into the plus minus 45, for example, with the increasing speed, you clearly see a decrease in consolidation quality. But for instance, on the more inner layers, you do not see that effect as drastically as you see on the top layers. But it's basically just to the fact that these materials sees with every layer we put on has a completely different thermal history as the outer layers. And yeah, therefore we need to find a process window where we can achieve the best consolidation quality for each type of material. So we started that iterative process to quickly evaluate and take the measures and changes on the trials that we are running. What's also really important is due to the fact we use semi-crystalline polymers, we want to use that benefit and have the highest crystallinity possible in the parts to get the highest mechanical performance as well, the chemical properties, which are really relying on the crystallinity level in the final part, in the application, to increase properties such as strength, stiffness, and for sure resistance against aggressive fluids. If you look into oil and gas applications or aerospace, like influence of potential oils, de-icing fluids, whatsoever. So therefore, the high crystallinity level is really important. What we did is for all the trials we did separate runs of TSC analysis. Not sure how familiar you are with that sort of analysis. So basically, it's a thermal analysis method where you compare a reference sample with the actual sample from the part and can get a good feedback of the thermal history the part saw, and then you can see different effects such as the melting, what you see on the right side, the high peak, or glass transition temperatures, and as well what we see on the left side when we look at the 50 meter per minute winding speed, we have a cold crystallization peak. That means on the winded samples we produced, we did not achieve the same high crystallinity level when compared to what we have on the right side, the curve from a static press panel. So we compared it to all the background we have with qualification work based on flat panels and coupon testing. And there we have we have not such a cold crystallization peak. The issue with the cold crystallization is that you already have a certain level of crystallinity structure, and then if the material sees another heating phase, even below melting, during the application, new crystalline structures will develop, which are not in the same, let's say, aligned as the original crystallization, the crystallines where the spherulites started to grow. We did that comparison as well for the different speeds shown for the microscopic analysis. Here you see, if we look into the first 3 ones, the 50 and 20 and 25, if we take into account the variation in the results, we could say they're all on the same level. So that's all in percentage to the fully crystalline sample from the static press on the right. And if we increase the speed even more, we see a decrease in the final crystallization level. But nevertheless, it's not on the level where we want to be, because we want to have the best possible mechanical properties and find the right setting for each material option. Therefore, now we are also looking into other speeds and adjust based on the polymers used in the different tapes. As a quick summary, what were the benefits out of the work and the ongoing work we do? We get a better understanding from the material side and from the processing side, combined to find a robust process which helps producing the best part quality based on the various customer requests, and also taking into account the economic values. If we find, let's say, an improved processing speed with regard to the automated processing route. What's still ongoing, as mentioned, this was just for the peak materials. We look at the Inometa PK materials and PPS furthermore, and we'll also do more evaluation with regard to how other parameters have an impact on final part quality, such as the winding angles and gap settings, because if we, not every customer wants the same tube with the same diameter. If the diameter changes together with the angle, it affects also the gap settings in the final application. And after that, we also need, based on the specific customer requirements, we need to find a way to also do a mechanical evaluation. With the insights we get from just the visual inspection and the DC measurements, we can make some assumptions based on what we did with coupon testing, but nevertheless, we need to do for specific mechanical properties part testing to meet the specific customer requirements. To summarize, I think, sorry, collaboration as we do from material supplier and the part producer, I think is key to find the best possible setup to reduce development times for customer requests, and also build trust for customers who are new in the field of thermoplastic materials, because not all have the thermoplastic backgrounds and try to change from, for example, thermoset materials to thermoplastic applications. And therefore, I think that's really the baseline to offer the best solution for the final customer. That's basically it. I would also like to thank Markus and the team at Inometa for the work so far, and the colleagues in Teijin that are not here. But thank you very much for your attention.
Ja, vielen Dank, Herr Kube, Herr Hildebrandt. Ich mache es wieder auf Deutsch. Und aufgrund der fortgeschrittenen Zeit müssen wir leider auf Frage und Antwort verzichten, aber Sie sind ja sicherlich gleich noch etwas länger da. Sind wir da. Dankeschön. Super.